Okay, hello everyone. It's a pleasure to have you all here for our first colloquium of this year's TBS Colloquia series. Today we have Imre Bartos. He's a faculty at Florida University working with mainly multi-messenger things. He's a member of LIGO, LISA, and IceCube. And today he will tell us all about atypical electromagnetic transients. So please take it away.
Thank you so much, Priscilla, and thank you for the invitation. So this is going to be centered on gravitational waves, but with a focus on multi-messenger and what is possible with Rubin, hopefully. So just to give a little bit of introduction, when we think of gravitational waves, we used to say that it's a new window onto the universe. I feel like after 10 years of, almost 10 years after the first discovery, this is less new as it used to be, but it's still a alternative view on what is going on out there, where we can learn information that's different from what we can gain from electromagnetic or other information such as neutrinos. The typical sources we focus on are black hole mergers, neutron star mergers, combination of these, possibly supernovae. We haven't had those detections yet, but in principle, that's a very, very interesting direction as well. And the key is that the kind of information that we gain from these sources, from gravitational waves, is very different from what we can learn, because the mechanisms that produce gravitational waves are different. So if we want to learn the most about these events, we have to combine what we learn in the different channels, including gravitational waves, including electromagnetic. And the other interesting thing, I think that's useful to mention right away about gravitational wave detections, is that we are rapidly expanding our detection horizon, and in the order of 10 years, we can expect to basically see events from the entire universe, all the way back to the formation of the first star. So it's going to be not just interesting sources themselves, but also an interesting view across cosmic evolution, again, in the near future. So when we think of multi-messenger and gravitational waves, the main thing that comes to mind is the detection of a neutron star merger in 2017, a couple of years ago, which was detected across the electromagnetic spectrum, other than just with gravitational waves. And this event was extremely insightful, and we're learning a lot about what happens in neutron star mergers, and in particular, what they do, for example, the production of heavy elements through the emission of or drive of gamma ray bursts. So this was a very interesting phenomenon, and there's a lot to talk about in this context. And this is, again, the center of attention in general in multi-messenger astrophysics when it comes to gravitational waves. I'm not going to talk about this direction, primarily because there's so much being discussed, but instead I want to look at two alternative directions that I think are very interesting and exciting in connection with gravitational waves and multi-messenger observations. So to go from this first neutron star discovery, we are now in the fourth observing run, the middle of the fourth observing run with LIGO and Virgo and Kagra, although currently only LIGO is operational. Or rather, it's not, because we are in a commercial break, or in the middle of the 04 observing run. There is about a 2-month break, and we're going to turn back on very soon, continuing the observations. So this has been a very productive period that we are still continuing. So again, there's going to be about 1 more year of observation coming up in a few days, basically. To summarize roughly where we are, so before this observing run, right, this one where we are in the middle, nothing is published yet. So this is, we mainly know things from what happened before. But prior to this fourth observing run, just in the first 3 periods, we detected on the order of 90 binary mergers, including black hole mergers, neutron star mergers, and some other objects that may be one or the other. And as you see in this plot here, as a function of time, the rate of discovery expanded very rapidly. It started off slow and then accelerated as the detectors became more and more sensitive. And they are even more sensitive now in the fourth observing run. So this is continuing. Again, nothing's published yet, so I can't give you any specifics. However, if we just look at the public website for the LIGO, Virgo, Kagra public alerts, there's a list of candidates that had been disclosed publicly through GCN circulars with the goal that there could be interesting multi-messenger follow-up opportunities. So this is a place where one interested in following up these events can find the candidates with their direction, with their or localization, with uncertainty. A type of event that one can expect, for example, is likely a black hole merger, black hole. Is it a neutron star merger, et cetera, et cetera. So as you see here, there had been on the order of 80 significant detection candidates, which means that it's most likely real, although not guaranteed at this point. So basically the same order already that was detected in the first 3 observing runs. So this is again, very productive period where the sensitivity is growing. We now also disclose what's called low significance events that are not, highly confident to be real events, but for multi-messenger opportunities can be very interesting. So this is what, again, we can know about the current event. So this is an accelerating process as we go forward. Looking at what has happened before this 4th observing run, here you see the events that we've detected in the first 3 runs, where the x-axis is some measure of time, not necessarily to scale, and the y-axis is the mass of the object. These different 3 combinations are the 2 objects that merge into a 3rd object. So this is how you can look at this. And the blue circles are meant to be black holes that merge into other black holes, and the orange circles are meant to be neutron star mergers. So these are detections. As you see, the vast majority of our detections are black hole mergers with a few neutron stars, and some of those neutron stars are actually merging with black holes. So they are black hole neutron star mergers. As you see, there had been 2 published neutron star mergers. So this is the distribution. And of course, you see that there are these weird half blue, half orange circles, which are in a mass region where we can't decide whether it's a neutron star or a black hole. For the purposes of what we detect, they could be either ones. Now, basically, there are many questions we can ask, but just to ask a simple question about this event, if you want to identify the origin, the astrophysical process that produces events, which is one of the questions we can learn the most from. This is difficult for many reasons. One of them is that the reconstructed parameters, mass, spin, etc., is uncertain, right? We don't do these very, very precisely, so there's some uncertainty there. But more importantly, almost, the astrophysical models of how these productions of, for example, black hole neutron star mergers happen are uncertain. So for the same mass, even if we know it exactly, it's going to be possible to generate that event from multiple different types of astrophysical processes. So this is hard, and there's different strategies to deal with this. One of them is to look at distributions of events or many events, or look at special events or surprising events that are unlikely from some channels, some formation processes, and can only arise from others. So this is one way to approach this. Now, to this direction, there are actually 2 mass ranges that are unique in some ways. They are called mass gaps, the lower mass gap, so-called, and the upper mass gap. They are interesting because we don't typically expect compact objects to form in these regions. The lower mass gap is, we simply don't see these often, or there are no high confidence detections of these events in the Milky Way, at least, although there have been some interesting recent developments. While on the higher or upper mass gap, we expect stars to not be able to produce these, because if they grow too big, they basically explode before they could form a compact core, and so they should not leave remnants in this mass gap behind. So if we detect objects here, that can be one clue of what actually happened that ended up forming these objects. Okay, so what can actually form black hole mergers? And I'm going to start focusing on the black hole mergers for the first half, and then I'll get back to neutron stars towards the end. But I want to focus on black holes first, because again, this is the vast majority of our detections. And there are different channels how we can form black holes. Just to name the key directions, we can have what's called isolated stellar binaries, where we have 2 stars. Massive stars like to be in pairs or triples or in groups, and these, when they go through their evolutionary cycle and become compact objects, naturally can reside in binaries. And so they can form binary black holes directly. We can also have so-called dynamical encounters, when black holes get close to each other in an environment where there's many of them in a small volume, and there can be this random gravitational capture that forms binaries. There can be also more exotic ways to produce black holes, such as in the early universe, which are called primordial black holes. And finally, which is going to be the star of the show today, the special case where we don't just have a large or dense population of black holes in galactic nuclei, but we also have an accretion disk that feeds the central supermassive black hole that can interact with these black holes and form interesting binaries and multi-messenger counterparts. So this is another direction or process that can form black hole mergers that we detect with LIGO, Virgo, and Kagra. So to focus on this last option, so why would this work? Why would there be black holes here? So there are two reasons or two ways how we can end up with black holes in the AGN disk in active galactic nuclei. One of them is there can be star formation, so there can be just black holes that are born through stellar evolution within the AGN disk. But probably more importantly, the disk itself can capture black holes. The way this happens is the black holes that are densely populating the central region of the galaxy, near the supermassive black hole within the inner parsec, basically, due to mass segregation, heavier objects move in, lighter objects move out. In this dense population, as the black holes crisscross the AGN disk, they interact, they basically experience friction that slows them down in the direction perpendicular to the disk. And some of these black holes with reasonably small inclinations can move in, basically align their orbits with the AGN disk within the lifetime of the disk itself. There's some indication that this happens observationally, for example, unrelated to gravitational waves, for example, in the there's indication for the dense population of black holes in a setter. For example, the detection of a large number of actually binaries near the center of the Milky Way in 2018. So we know that these populations exist and they can interact with the disk and align their orbits. So this is how we end up with some of these black holes in the disk. But this is not the end of the story. Once the black holes are in the disk, they can actually migrate inwards within the disk due to basically a pressure gradient that they experience. And effectively, we are squeezing these black holes into a smaller and smaller volume. We already can have a large density of black holes in the center of the galaxy, but then they are squeezed into a 2D volume in the AGN disk, and then they can be squeezed in even further as they are moving towards the center through migration down to a small distance from the central supermassive black hole. It's not exactly clear how far this is, but it could be anywhere from a few hundred Schwarzschild radii to maybe 10 to the -2 parsec, depending on the interactions they have in this environment. So basically, this region works as a black hole assembly line that brings black holes from the center to smaller and smaller volume that will eventually merge. Not only does the AGN disk bring these closer, but also the disk itself and the gas can help capture and form binaries. It's what's called gas capture. Basically, in this gas-rich environment, the disk itself can interact with the black holes and slow them down, make them form a binary quicker, and then merge much quicker than they would do just through the emission of gravitational waves. Not only this, but in addition, as these black holes are being brought closer together, the merged black hole, if this happens, actually will not end up leaving the system. So that can stay in the same location. So we can have a series of consecutive mergers which form heavier and heavier black holes after each merger, since the remnant stays in the vicinity of where the AGN disk brings in the consecutive black holes. So there can be interesting observational consequences for this in particular. One consequence is higher mass. So again, mass segregation itself that brings in heavier objects to the center will favor heavier black holes. Also, there's accretion in the disk that can be added here. But finally, this series of mergers, which is called the hierarchical merger, can make the black holes' masses heavier and heavier. So this is one observational consequence we can check directly with gravitational waves. If we find heavier black holes, that can be an indication that something like this is going on. Another option is higher spin for these black holes. If we have accretion, or if we have these series of hierarchical mergers, both of them increase eccentricity, increase spin. For example, the merger of two black holes of the same mass will end up producing a remnant black hole with a dimensional spin of roughly 0.7. So this is something where the spin can be high. This is something we can look for through gravitational waves as we can reconstruct the spin of these objects. And actually, there had been such detections of heavy objects. To mention one, which is an interesting indication of this possibility, is the event called GW190521 that was detected, as the name implies, in 2019. This was a binary where both masses were very high, what we would consider in this upper mass gap. So it's possible that these heavy masses, since if we understand star formation and stellar evolution correctly, had to be due to something else, which is possibly due to previous mergers. Also, while spin is less well reconstructed from gravitational waves as the mass, it looks like this event also had high spin for both of the black holes, which is also an indication of this possibility. Not only this, but the spin itself was not aligned with the orbit, which is also something we don't expect from binary stellar evolution. So all these are, if not conclusive, but supportive of this possibility that this event was the result of previous mergers. Now, why should you be interested in this? So the reason is that this is not the end of the story when it comes to observing these events. In particular, the merger of black holes in AGN disks is special because while black holes just by themselves would not do anything but the radiation of gravitational waves, if the merger happens in a gas-rich environment, then there is fuel for these black holes for accretion and then consequently for the production of a multi-messenger signal, primarily an electromagnetic signal. So how can we think about this? Basically, it's not that simple. And the reason is that if a black hole binary is formed in the disk and is orbiting, basically, even though there is accretion, the process will be such that the accreting black holes will produce an outflow that basically will create a cavity around these black holes. So in the sort of long term, in the evolution of this binary, this can be a balancing process where the actual accretion rate due to the reduction of the accretion due to the outflow may not be that significant, which means that it may not be something that's easily detectable from a large distance. However, once the merger happens, once these black holes actually merge into one black hole, they can experience what's called a recoil, gravitational wave recoil, which basically kicks the remnant in some direction with a potentially high velocity up to on the order of 1,000 kilometers per second, typically somewhat lower, in a direction that could be in the AGN disk. So basically, the recoil itself, the merger itself, can transition the black hole from this cavity, which is roughly emptied out, to a region of the AGN disk that's actually more dense. This will start a much higher accretion rate for a period of time until a new cavity is formed around the new black hole. That can lead to interesting electromagnetic counterparts. Basically, for high accretion can lead to outflow, potentially even jets, and this can be either producing an electromagnetic signal through the shock breakout itself, or shock cooling as there's an adiabatic expansion once this outflow broke out of the AGN disk. These can both lead to emission that can be, well, first of all, modeled, but can also be potentially detected. These detections are either X-rays, so typically shock breakout itself has an X-ray component, but these can have a corresponding optical component that can be very interesting to observe with optical observatories. To be more specific, or actually to put this in perspective, there has been actually work to identify such possible counterparts already with the previous observing runs of LIGO Virgo. At that point, it was just LIGO and Virgo. Kager was not yet part of the team, and basically there had been a possible counterpart identified in 2020. So this was after or actually soon after the end of the O3 observing run. And the Atypical transient facility followed up basically all the black hole merger events it could to identify possible counterparts, specifically in AGN disk. So basically what this search was looking for is unusual AGN activity in coincidence in time and direction with the black hole mergers that LIGO had been seeing and announcing publicly through GCN notices that we had. And it turns out that the first discovery or identification of such a candidate, again, it's not 100% certain at this point, but the first candidate actually happens to be this GW1905-21 event, which I just talked about as a possible, as a heavy black hole merger that is possibly from an AGN disk. So this was a signal that you see here on the right side as a function of time in G and R bands. Okay, so this was roughly, they started roughly 2 weeks after the merger in time, a couple of gigaparsecs away. So this was a distant discovery and lasted about 2 months. So this was a long signal, and that was basically what was expected from these counterparts in terms of duration, in terms of luminous, etc. So this could be modeled at the time. Now, since then, since this first somewhat higher confidence, actually, sorry, just to mention, also there's this map here I'm showing just to give you an idea of how these reconstructions happen, right? So once we look at an AGM, we know its precise direction. However, on the gravitational wave side, we typically have a larger error region. In this case, as you see here, this was a substantial part of the sky that was the possible direction of this source. So gravitational waves are not as precise when it comes to direction reconstruction as you know, what we can do with optical or even gamma rays for the most part. So this is an uncertainty, which means that it makes it more difficult to identify counterparts, partly because of the higher false alarm rates, but also partly because these directions have to be covered, right? So someone has to actually look at all possible directions to cover this sky area. And this is why these kind of follow-ups are best suited for large deep all sky surveys, basically, where we're not targeting something with a small field of view telescope, but actually do a survey over a large area with a decent cadence. So we see this variation over time. Again, the order of time we are talking about here for this event in particular, and what we expect typically is order of, you know, weeks essentially. Okay, so it's a longer term observation, definitely. And also, this is also comes down to how we can separate these possible signals from the background. So understanding long-term AGM variability is critical so that we know that this is something expected or this is something unexpected. In this case, the ZTF group concluded that this is unexpected. They assigned a fairly high significance to this event. And then afterwards, actually a couple of years later, they found 8 more candidates, which are not statistically conclusive. However, they found indications that these, at least a subset of them, might be also related to gravitational wave events. Again, they were all that they found were all in time and in direction coincident with gravitational wave events that LIGO, Virgo, and Kagra found and released publicly. So what can we do with this information if we find such an event and basically have this light curve for these events? Well, this can be super useful because it's not just that we have identified that this is possibly a AGN-assisted black hole merger, but actually by knowing these parameters, reconstructing these parameters, we can also say something about the properties of the source and the properties of the environment. So not just that this is AGN, not AGN, but also, for example, accretion rates, other properties, AGN luminosity, et cetera, all these can be changing what we see in terms of the light curve. And therefore, if we see the light curve, we can reconstruct them through this detection. So to give you an idea of how this roughly looks like, we did this work last year, but it was just accepted in FJ. But basically, if we take the parameters that affect or that can be measured by light curve, such as delay time between the onset of the optical counterparts and the merger itself, the duration, how long we see this time frame, etc. Basically, we can use these to reconstruct the properties or vice versa. If you know the properties, we can predict what light curve we are expecting. And here you see a few examples. So basically, the 2 processes I mentioned are a shock cooling and shock breakout. Shock cooling for optical is more relevant. And here you see that basically, depending on the exact parameters, we have this decent flux of optical counterpart this is a source a brightness at 3 gigaparsecs. Okay, so this is a typical distance source, or even on the higher end for what we see with gravitational waves, and even there this can be detected with, for example, ZTF and Rubin, of course. So this is something where the brightness can actually be very high. And to basically demonstrate how this works in practice, right? I mentioned that there are these 8+1 candidates, or one more likely and 8 candidate events. We can use this to reconstruct what parameters we are expecting. And again, these tell us about the parameters, but ultimately also, if we, for example, if we find parameters that are unrealistic, that we're not expecting in AGNs from the modeling of these mergers, then that can also, for example, differentiate if one of these is real or not, right? If you find unreasonable parameters, then they may not be real just from this information. So doing this, and this is one example I want to highlight here for these 8 events that I just mentioned that were identified as possible counterparts, we can compare what we expect from the detection of shock cooling, what we expect from detection if it's due to breakout emission. And for example, if we model these with shock cooling, as I mentioned, which I'm showing here, we find that the corresponding distance between the merger itself and the central supermassive black hole is on the order of 0.1 parsec, essentially, which is very much in line with what we expect. I would say we would probably expect somewhat lower distance typically, but the 0.1 parsec is reasonable. However, for example, if we model these light curves with breakout emission, a shock breakout emission, then the corresponding distance that would require be required to produce the light curves is something like 1 to 8 parsecs, which is way too high for this. We don't expect any mergers at those distances. So just from this analysis, we can say that if these events are actually real, then the emission that we are seeing, the light curves that we are seeing, could have not come from breakout emission. At least it's highly unlikely. So there are these. So basically, once we detect these light curves, there's a wealth of information we can gain about the source, about its likelihood of being a source, about the origin of the black hole mergers, etc., the properties of its environment. Super useful information. Moving to the other topic I wanted to mention. So this was, again, AGN-assisted mergers connected on the observation side with the upper mass gap, for example, although clearly there could be events that are lower mass. It's just harder to differentiate those without a multi-messenger signal. However, there is this lower mass gap as well, where we can have special information about the origin of the sources if we detect something here. And as you see, there had been one here, discoveries with LIGO that had been published so far that were in this mass gap. So they are something potentially very interesting. And if you look at the masses here on the in the middle plot, or the left plot out of the 2 plots here, actually, sorry, the right plot. I want to mention the right plot here, which is the object with the mass gap. So these were mergers that had these objects which were in between this 2 to 5 solar mass range, and they merged with a much heavier black hole. So the left one here shows the mass of the black hole, but that's not the main thing I want to focus on here, but the mass of the mass gap object. So actually, both of these events, one of them is a high confidence, one of them is somewhat less confidence, but both of them had a reconstructed mass on the order of 2.6 solar masses. Okay, so it's not just mass gap as in 2 to 5, but specifically the masses we reconstructed were roughly 2.6. Here, this is, so on the right side here, this is M2, that's the mass gap object in solar masses mass, and the orange dot dash line here is the mass distribution, reconstructed mass distribution of one of these events, and the less well reconstructed event is the other one, which is the blue dotted line. Okay, and the reason there's 2.6 solar mass, again here there's more uncertainty in the second event, but the first one is very much centered on this 2.6. The reason this mass particularly is interesting is that it's very much the same as what we have if we look at the total mass of neutron star binaries that we see or we know of in the Milky Way. Okay, so neutron stars can be within a wide range of masses from 1 to 2 point something, 2 point few, maybe 2.2 solar masses. However, if you look specifically at binary neutron star systems in the Milky Way, for some reason they all are centered around this 2.6 solar mass total mass, or roughly 1.3 solar mass for individual neutron stars in this. So there is this mass selection that appeared at least in the binaries that we see in the Milky Way to center the total mass around 2.6 solar masses. it is definitely heavier than what we expect from neutron stars themselves, especially over a long period, right? Neutron stars can survive with heavier masses for some time, but for longer term, the maximum neutron star mass is something like 2.2 solar masses, so this is heavier than that. So something had to happen with neutron stars to form this, and it could be either accretion or it could be the merger of two neutron stars, which would end up producing this 2.6 solar mass event. And this is a very interesting possibility, because then it can tell us something about how these events formed. If this is really a merger, then it had to be a merger that then ended up merging with a heavier black hole. So just to take a step back and try to think about what are the possible origins of this interesting mass range, right? So one of them that I'll mention here is if we have, for example, a triple star system, which is again common for massive stars, they can end up going through evolution so that two of them form neutron stars and one of them forms a heavier black hole. If the neutron stars merge and then they merge with their tertiary black hole partner, then that can lead to the observation we made with LIGO, right? So what LIGO Virgo saw was not the first neutron star merger, not necessarily at least, but after this first merger, we saw the remnant merge, if this is a remnant, with a heavier black hole. So this is one possibility. The other option is accretion, and for example, in AGN disks, one could experience accretion onto the neutron star that could increase its mass to this range. However, the reason, even though I like AGN disks, the reason I'm not suggesting that this is a likely possibility is twofold. One of them is that primarily we expect black hole mergers in AGN disks, much less neutron star mergers. There could be some neutron star black hole, but not neutron star mergers for the most part. Simply mass segregation ends up producing or moving many more black holes in that region. And the other reason is that if we have any accretion process, then the accretion has no reason to produce exactly 2.6 solar masses. It could be anywhere in the, say, 2 to 5 solar mass range. So if we see these 2.6 solar masses, that's unusual and it's unlikely to be produced by accretion. And third, it's possible to end up with these mergers. Again, if it's two neutron stars, then it's basically a hierarchical merger where with first neutron stars merging, then the remnant merging with a black hole. The other possibility is that these consecutive mergers happened in a dense environment, dense referring to a large number density of black holes and neutron stars. This is a possibility, and this is a tricky situation because on one hand, in such a system, one would expect that, again, there is mass segregation here as well. So one would expect more black hole mergers than neutron star mergers. So if we had this neutron stars merge and then merging with a black hole, we would expect more of these in a way that we have two black holes merge and then it merging with a third black hole. So you should have more black hole mergers than this neutron star merger then merging with something else. However, this is not what we see. The rate density of mergers is about the same what LIGO, Virgo, and Kagra are detecting for black hole mergers overall, independent of the origin and the reconstructed rate density of these events with the mass gap merging with a black hole. Okay, so that's a big question mark. The reason I'm not saying that it's ruled out, or the reason there's support for something like that, is a recent discovery that I think was published maybe 2 weeks ago or a little more, of a basically a mass gap, likely mass gap object that was found in a binary in a nearby globular cluster where the reconstructed mass of this object was 2.7 solar masses. So basically consistent with this neutron star merger scenario, although again, this is still a range which is not approved by itself. But nevertheless, there was this recent event found in a globular cluster nearby. So it could be, and because it was in a binary with a neutron star, it's possible that there was a process that produced this. So there are lots of interesting question marks here. But if this is the first scenario that I mentioned here, which is that we have a triple system, which we do have, and we have two neutron star merge and then merge with a black hole, then there are some very, very interesting consequences that are relevant. First is, or just to sort of make it more general, right, we can have events in a mass gap from this process, but also if this is the case, then there should be a possibly large fraction of neutron star mergers that happen in triples as opposed to in just binaries. And the reason is that only a tiny fraction of triple systems should end up undergoing double mergers, where we have the first merger of the neutron stars and then merging with a black hole, simply due to the dynamics of a triple system. And so if we see a particular rate of the secondary mergers with the black hole, there should be a lot more mergers that are actually the mergers of the neutron stars only. Okay, so if this is the case, then we should have a good fraction or a high rate of neutron star mergers that happen in these triple systems, especially at high redshift, which is interesting by itself. And another consequence, and particularly the consequence that is relevant for optical observations, is the following. When we have a triple system with the neutron stars, the interaction with the tertiary black hole means that the neutron star binary can become eccentric due to the causative mechanism that will basically exchange eccentricity for the binary to inclination that the binary has with respect to its orbit around the other black hole. Eccentricity means two things. First, it can merge much quicker than it would just through the radiation or gravitational waves. And if it does merge quicker and it has an eccentric orbit when it merges, it actually the quick is not relevant here, but if it merges when it's eccentric, that basically means that the production of heavy elements when we look at the dynamical ejection from this object can be very different, and can explain or can produce something other than what we expect from standard circular neutron star mergers. Okay, to be more specific, we carried out simulations of these highly eccentric, potentially highly eccentric neutron star mergers. And what we found was that the dynamical ejection, which is one of the two ways neutron star mergers eject matter, the other one is basically through winds from the accretion disk. The dynamical part, which is basically how much matter is just ejected while the merger is happening dynamically, can be on the order of 10 times greater, depending on eccentricity, than what we expect from a circular merger. Now, when we look at the light curve from a kilonova, this is affected, and this is not fully understood at this point, but this is affected separately or differently by the dynamical ejecta and the ejecta from the disk itself that's formed around the remnant. And basically, the dynamical ejecta is meant to have a higher electron fraction. So basically, it will end up being on the bluer side of the emission spectrum. So what we expect if we, through this process, simulate this, but in general, if we just increase the dynamical ejecta part while keeping the ejection from the disk the same, what we'll have is a earlier and bluer emission than what we have otherwise. So what you see here on the bottom right is different possibilities. The blue line is what you have in this simulation with some assumed electron fraction. Normally, this is what we would expect as a time evolution of the emission if the collision is circular, which is typically what we expect. If we increase the eccentricity first to this green line and then to the even more to the red line, what you see as the main difference is that there's going to be a early blue component or early blue bump, if you will, that is produced basically on the first day of the emission. So very early, which is, again, somewhat harder to track. So this is something which has a very specific prediction for this channel, for the optical, which is not just special, but also is difficult to detect normally because as we saw for the first neutron star merger discovery, there's typically a delay with which we can detect these events. Simply, you have to find the direction over a large sky area. And so we expect to see many of these events only with a delay, except, of course, if we keep monitoring the whole sky and make this all automated, which is, I think, a very exciting possibility for Rubin in particular. So looking a little bit forward, and I didn't check the time, how I'm doing with time, but assuming I am, yeah, I'm doing very well, thank you. Okay. Looking forward, we are in the middle of this O4 observing run, as I mentioned, and LIGO is off now, but we'll be turning back on very soon. Currently, we don't have Virgo and Cognitive running. They are trying to get back on online so they can join this observing run. It should last for another almost 1 year, so there's plenty more discovery to go. as we are going to be publishing the results that we already have, but have not been published. But also looking forward, this is not just the next year, but in the next, I would say 3 years, we're going to be upgrading after this this current run. We're going to be upgrading the detector for the consecutive 2 more years. Upgrading here means improving the detector, changing some of the hardware, improving some of the hardware to make it even more sensitive. The way we typically measure this is by how far on average we can detect a neutron star merger. So as you see now, it's on the order of 160, 180, 190 megaparsecs, and this will grow by basically 50%, okay, or more for the next observing run 05. 50% in sensitivity or distance means 50% or 150% cubed, right? So it's a factor of 3 more detections or a factor of 3 higher detection rate, okay? So it's going to be quite a few events over the next 5 years, which is, I think, very interesting for Rubin as well. And looking even further, just to mention for the context here, next 10, 15 years-ish, again, we're going to have 3rd generation detectors both in the United States and Europe. Most likely, the locations are unknown at this point. And these are not just going to be farther. So the way we will describe the distances will change very much, because effectively, especially for black hole mergers, these detectors will be sensitive to the entire universe. So this will be a very different order of magnitude. There will be no point discussing the horizon distance anymore, again, in a very reasonable 10, 15 years time frame. So super interesting. So to conclude, the 2 directions I outlined or highlighted that I want to emphasize as the takeaway. First is the possibility of black hole mergers in agent-assisted or agent-assisted mergers. This is something which is, again, partly relevant because there is a very rapidly growing rate of discoveries in gravitational waves, and most of these are black holes. And some of them have indications that are or could be coming from agent-assisted. So this is a support for this possibility. And if this is possible, or this is what actually happens, this is a very exciting multi-messenger opportunity for black hole mergers that is typically, and for other channels, not considered. If this is the case, the optical counterparts, if we detect these, can give us a lot of information that is very relevant for different questions. It can confirm the origin of different events. It can be used, as I showed, to reconstruct the properties of the source. It can be used to say something about the environment in which these mergers happen. And these follow-ups for black hole mergers are difficult, and more difficult than for neutron star mergers, because of the larger distances and because of the larger sky areas that we have to cover. So ideally, suited is an observatory that does long-term observation over with a large field of view and with a regular cadence. I think this is a very interesting target for Rubin in particular. And the other channel I mentioned was the possibility that triple systems end up producing 2 consecutive mergers, first with 2 neutron star merging, then that can merge with a black hole and neutron star. There is some observational indication that this may happen. LIGO discovered 2.6 solar mass object that could be doing this. And if this is the case, if we have these triple systems, this can have very interesting observational and just astrophysical consequences. For example, due to the fastness of these mergers, it could explain why we see earlier process production in the universe. It could also produce a peculiar type of kilonova with an early blue bump, as I called it, which is something that can be differentiated from the other neutron star mergers that we are seeing if there is a high enough eccentricity at the time of the merger. And so because this happens, this differentiation happens very early, it's actually difficult to see in general, because we have to look at the source very quickly, again, because of the localization, because of, if doing a follow-up to gravitational waves, this can be difficult. This is something that's also a very interesting target for all sky large field of view observatories such as Rubin. I'm going to stop here. Thank you very much. Happy to take any questions.
Thank you, Imre. That was great. You managed your time very well and delivered a very interesting talk. Thank you so much.